Okay, so for 3.1, right, so we go for current and potential difference. So this chapter is actually about the electricity. So current and potential difference, right? So in this topic, we will learn about what is electric field, what is we have to define what is the strength of electric field, okay, and also the behavior of the charge particle in the electric field, okay, and we have to define the current and also the potential difference, right? So the first one is to explain the electric field. All right, so someone not using the okay. Okay, so diagram 7.11 shows a light bulb is connected to a power supply. Okay, so what makes the light bulb up? Okay, sorry, what makes the light bulb light up? Okay, so of course this is actually because there is a flow of electricity, right? So it makes the light bulb to light up. Okay. All right, so this is the Van de Graaff generator, right? So this is actually, I think you already learned, okay, during science form 2, I think, right? There will be that the positive charge particle and negative charge particle, right? And then this is caused by the friction, right? Okay, and then if you come near to the Van de Graaff generator, okay, so your hair will like, like straight up like that, okay? So this is the video to show for the Van de Graaff generator. Okay. Shake your head no. You are really mad. Tell them no. This should be a good one. Tell them right, no. So this is the example. Yeah, okay, if I use the Van de Graaff generator. Okay, so actually there is a charge right between the hair here. So the same charge will repel, right? So it become like this. Okay, so electric field. So this is the example. Okay, in our real life. Okay, the to shows that there is a electric field. Okay, in our surrounding. Okay, so a fine streak of tap water is bent when the charge comb is brought near it. Okay, and the hair is attached to the charge balloon, or you can use your comb to attract the paper. Okay, and also a charged drinking straw or move closer to an approaching finger. So this is the example in real life. Okay, you can do this as a simple activity. All right, so when a charged comb is brought near to a fine stream of tap water, the stream of water bends towards the comb. Okay, so this phenomenon indicates the existence of electric fields in our daily life. All right, so what does it mean by electric field? So electric field is the region, okay, is the region where when a charge experience an electrical force. So let's say if you put an object here, okay, that will experience the electric force here. So you have to know the positive charge is actually the direction is coming out. Okay, it's coming out from the positive charge, right? While the negative charge, it will be the direction of the electric charge will be going inside to the negative charge, right? So this one you need to know and you need to draw. Okay, and you can see the line of the magnetic fields, right? Okay, the line of magnetic field does not um it does not like uh cross each other. Okay, it's not across each other. Okay, so the positive we go to the negative because the positive and negative will attract. Okay, we attract the different charge will attract each other. So you can see the positive goes out while the negative charge go in. Okay, so the meaning of the electric field, whenever they use the word field, there must be the word region. Okay, later you will learn about the magnetic field. So the magnetic field is the region. Okay, so every time they use the word field, okay, the meaning of should have the words region. Okay, so the region where a charge experience an electric force. Okay, so that's the meaning of the electric field. Okay, so this is the simple experiment, okay, to show that the electric fields, okay, positive and negative, right? Okay, so this is the, no, this is only the picture.
Assalamualaikum rakan guru sekalian. Sini saya nak tunjukkan corak medan elektrik menggunakan set seperti ini. So untuk set ini saya perlukan power supply high voltage, kemudian mangkuk pija, kemudian minyak
Okay,
masak.
they put oil.
Minyak masak. Jangan terlalu banyak, sedikit pun tak sesuai. Okey, kemudian kita taburkan bijian di atas ni.
Okay, so you can see this one is a positive charge, okay, and this one is connected to the negative charge, right? So
Okey, kita cuba onkan keran kuasa. Lihat. Okey. Ada perakan.
so you can see, okay, the serial. Actually, they put serial inside of it. Okay,
Kita naikkan voltage.
so increase the voltage. So you can see there is a movement.
Ada bijian ni bergerak.
Okay, there is a
Daripada
movement.
terminal negatif, ini negatif, ke terminal positif.
So you see there is a positive goes to the negative.
Okey. Tidak begitu jelas ya. Okey, ni corak yang pertama. Apa kata kalau kita ubah dalam bentuk plate ya.
Okay, so this one not so clear, right? This one actually when they change it to plate. Okay, so this one you can see there is a movement. Okay, this one is the negative, positive.
Campur lagi.
So you can see there is a movement. I think for the plate it's easy to see than the one that is using only one charge, right? Yeah. There is a movement of charge here.
Ini terminal negatif, ini terminal positif.
Negative, positive. So negative, positive. So it should be positive goes to negative.
Okey, bijian ni membentuk urat daya.
So that's the electric field. Okay, for the plate. Okay, for the plate. Right. Later we will learn how to draw it. Right. Okay, so this is actually what the experiment about. So the first one you can see they use 2 points of electrodes, okay, positive and also negative, okay, and another one they use a point, okay, only 1 point of charge here, but another one is a plate, okay, the negative one they use a plate, okay, but this one they only use like 1 point of charge only, like this one they say positive and this one negative, so only one charge like that. Okay, but for this one is a positive, one charge like that, but this one they use a plate of electrode. Okay, and this one they use both of it, they use a plate. Okay, positive and negative. So how we want to draw? Okay, how we want to draw for the electric field for each of the diagram. Okay, so you already know that actually positive, the direction of the magnetic field is going out. Okay, while the negative is going inside the charge, right? So it has to be positive goes to negative, right? So you have to draw the line, okay, positive to negative. Okay, wait. Positive goes to negative. Okay, the minimum line, it should be three lines of magnetic fields, right? Means, okay, it should be like this. Okay. Right. So this is the electric fields for the 2 points of electrode. Okay, what if they use 1 point of electrode, another one they use a plate of electrode? So the positive will go out, right? So it goes to the negative charge. Okay, we go to the negative charge. Okay, and this one. Okay, so this is for the point of electrode and also a plate of electrode. So what if both of it is a parallel plate? Okay, the positive and the negative, they use a plate. Okay, so this one positive goes to negative. So it's only like this, a straight line. Okay, alright, so if you want to draw others also can. Okay, so this one, they say it's going in. Okay, it's up to you. But usually they only draw like this. Okay, so we go from positive to negative. Okay, so this is the electric fields. Okay, right. So this is the result for the positive charge is going out. Okay, the negative will be going in the directions. Okay, and this one is the plate positive to negative. Okay, and this one is negative to negative, because negative there will oppose, right? They will oppose to each other. Okay, so it will be like this. Okay, they will not go from negative to negative, no, because they have the same charge. Okay, so example, let's say if I change it to positive, positive. So what happened here? Okay, it's same, but the direction is different. Okay, the direction is different. Okay, it's same, but the direction is different. Okay, so positive mean is going out. Okay, like this, and also same like this. Okay, only the direction is different. Okay, but the way to draw is same. All right, and for this one, they have a different charge. Okay, so when they have a different charge here, you can see there is a positive goes to negative because it attract each other, because they have a different charge. So different charge is attract each other. So the positive we go to the negative. Okay, and for this one, okay, one use a point electrode, another one use a plate. So the positive we goes to negative like that, right? Okay, so this is the electric field. So you need to know how to draw it, because sometimes they will ask you to draw whether come out from paper 1 or paper 2. So actually it's very easy as long you know that two basic things. The first one, the positive, they go out. Okay, the direction we go out, while the negative, the direction we go in. Okay, and if they have the different charge, they will attract each other. Okay, means they have to go from the line positive to the negative charge. If let's say it's the same charge, it will be opposed each other. So you have to draw it like this. Okay, that will not go from negative to negative. No. Right. So this is the electric fields, okay, in the charge. Right. So this is another example. Okay, so you can see negative, right, and positive. This is using a plate and the positive. So it's basically it's the same. All right, so discussion why EHT power supply is used. Okay, so why we use the EHT power supply? It means high voltage, right? Because we need to get a strong electric field. Okay, so we can see actually what happened, okay, to the electric field. Okay, and what happened to the parallel plate electrodes when the EHT power supply is switched on? So the two electrodes will be at different potential, and electric field exists between the two electrodes. Okay. And why does the sprinkle semolina powder form a certain pattern when the EHT power supply is switched on? So when semolina powder is placed in the electric fields, okay, it experiences an electric force. Okay, so the pattern formed by the semolina powder shows the pattern of the electric fields. So mean after you switch on the EHT, the power supply, okay, then the semolina powder will start to move. Okay, so why it's moving? Because there is an electric charge. So the movement is actually influenced by the electric charge, right? So then we follow what is the pattern of the electric charge, right? And another one for number 4, why cooking oil and not water is used in this activity? Okay, so cooking oil is not a good electric conductor and it's not an electrolyte. Okay, so essentially it's for safety lah, right? Okay, and why metal plate is used? Okay, so of course metal plate, you have to use a metal plate because you need to make sure that the electric charge is flowing, right? So now then you can have a pattern, right? Then you can form electric field. So let's say if you use a plastic, you know plastic cannot the electric cannot flows through it, right? So you cannot get the electric fields, right? So that's why we use a metal, because the metal is a good conductor, mean it can means the currents can flow through it. Okay. And number 6, the pattern formed by the semolina grains is called as electric field pattern. An electric field is represented by the series of arrow lines called an electric field line of force. What does the line indicate? So the magnitude of the electric fields. Okay. So if there is more, let's say if I compare, right? I give you a diagram. This is this diagram. Okay. They say I'm taking this as example, right? Taking this example, positive and negative. Positive and this one negative, right? And the electric fields, okay, is only this one. So if we compare this diagram and this diagram, so this one has less magnetic field than this one. So it shows that this one, the magnetic field is lower than this one. Okay, means if there is more electric field line, means there is a stronger of electric force there. Okay, so this one, if we compare, of course, the below part, the below one here got the stronger electric field because they got more electric field line. So this actually also can be used to compare the electric field strength, right? So this one is weaker lah. The electric field is weaker than this one, okay, because they got a few lines, okay, compared to this one. Okay, and another one, if there is close, all right, if the electric field is closer to each other. Okay, so let's say if I have another example. Okay, if I have another example here. Okay, like this. Okay, so this one, if we compare the line also, we already know, right? This one have the stronger electric fields, okay? The magnitude is stronger, okay? But you can see it's closer to each other. So when it's closer to each other, means he has a stronger magnetic field. So it's actually, you know, the strength you can use, we can see it by the lines of the magnetic fields also, and another one is the distance between the magnetic fields. So if it's much closer, mean it has a stronger magnetic field. Okay, and another one is a number of line of magnetic fields. There is more lines of magnetic fields, mean there is a stronger magnetic fields there. Okay, this one we already discussed. Okay, so it says here the electric field line of force never cross each other. So you see my drawing, okay, the line is not crossing each other between the magnetic field. So describe the direction of the electric field line of force in the activity. So the direction has to go from the positive charge to the negative charge, right? The positive go out while the negative, the charge will, the line of the direction of the charge we go in, right? So how is the strength of the electric field indicates in the field line. So the electric field is the strongest if the electric lines of force are close together. This one I just described just now, right? The distance between the line, it is much closer, right? Means it has a stronger magnetic field. Okay. All right, electric field strength. So assume the positive test charge Q is placed in the electric field. So let's say this is the positive charge, right? So I put a positive charge, okay, in these electric fields. Okay. So what will happen? So you already know positive and positive, it should be opposed each other, right? Will be opposed each other. So when you oppose each other means there will be a force, right? A force that make the charge here to move, okay, away from the positive charge because they have the same charge, right? So the force that used to push away the positive charge here is called as a repulsive force. Okay, so the repulsive force is actually we can count by using the formula E is equals to F over Q. Okay, And this one, let's say negative and positive. Of course, we know negative and positive, it will attract, right? So the force that being used to attract the charge here, okay, we call it as a attractive force. Okay, so attractive force. All right. So the electric field strength is a given point in electric field defined as the electric force acting on a unit positive charge placed at the point. Okay, so mean we use a positive charge only, right? We use a positive charge only. We put it near to the charge, let's say positive charge. Okay, then let's say it push it away, right? So we can find the electric field strength by using the formula E is equals to F over Q. The F is actually the repulsive force caused by the by the charge here, okay, to push the charge, the positive charge away from it. Okay, so it's actually E is equals to F over Q. All right, and this one, let's say if you want to find the to find the electric field strength here, but you need to use only the positive charge here. So the positive charge, when it comes to the negative charge, of course it will oppose, right? It will attract. So when it attracts, so what is the force that need, okay, that what is the force of attraction there? Okay, that used to attract the negative positive charge here to be closer to the negative charge. So the electric field strength here is same, is E is equals to F over Q. So the F here is actually the whether repulsive force or the attractive force. So what is the E actually? E is the electric field strength, F is the electric force, and Q is the quantity of electric charge. Okay, so basically they will give you the amount of Q here. Okay, so the SI unit for E is a Newton per coulomb because F is Newton. Okay, Q is in coulomb. Okay, so sometimes they use capital letter Q. Right, it's not called small letter Q, it's actually Q, capital letter Q. Okay, so the quantity of electric charge is in coulomb. Okay, and it should be N over C. Okay, so this is the first formula. So the test charge will experience an electric force. So this force either can be repulsive or an attractive force depending on the type of charged particle. Okay, so what is actually the type? So let's say we put the positive near to the positive, it will repel. Okay, let's say positive to negative, it will attract. Right? So this one can be, it depends lah, right? Whether positive or positive negative. So this is the first formula. Oops, sorry. Okay, the electric field between two opposite charged parallel plate is uniform. Okay, and the uniform electric field is represented by the set parallel of electric fields. So uniform electric field, you can see here the line is in uniform, right? Okay, so the electric field strength E produced by two parallel charged plates. Just now we learned for point, right? For the point charge, right? Point charge. And but for this one is for the plate, okay? For the plate. So for the plate, they use this formula. E is equals to V over D. Okay, so E is actually the electric field, okay, electric field strength, and V is actually the potential difference, right? So what is the voltage supplied to the to the plate here? Let's say this one we know we use EHT, right? We use a power supply. So let's say if I put 4 volt, right? So mean your V is 4 volt. Okay, so how much the voltage supplied to the plate? Okay, and D is the distance between two parallel plates. So let's say this one I put like 10 cm. So my D is 10 cm. Okay, but the SI unit of E in this formula is volt per meter. So for this one, mean you have to change it to meter by divide it with 100, or you can just simply 10 times 10 power of negative 2 is actually equals to meter also. Okay, I just change centi here to 10 power of negative 2. Okay, so the unit for this formula is V over m or Vm power of -1. So it's different if you want to calculate for the point charge. So for the point charge is E equal to F over Q. Okay, Q is the quantity of charge, right, in coulomb. F is the force, okay. What is the repulsive force? What is the attraction force? Okay, attractive force, okay. So this is for the point charge. Okay, but this one is for plate. Okay, E is equals to VB. So this is the experiment. Alright, so the first one they use the candle. The second one the candle. The first one they use a polystyrene bulb. Okay, so what is actually happened here? Okay, so I just explain it. You know. Okay, so the first one I explained about the polystyrene bulb, right? So this is the polystyrene bulb means they have no charge. Okay, they have no charge on it. Okay, but then right when I switch on the voltage here, the power supply here, okay, and I touch the polystyrene ball, let's say this positive charge, okay, okay, because how do I know this one is positive? Is from here, okay, this one is positive, and this one is negative, okay. All right, so let's say I touch the polystyrene ball to the plate P, okay. So what will happen here, right? So all the positive charge, okay, will go to the polystyrene ball. Okay, so when it goes to the polystyrene ball, now the polystyrene ball have positive charge, right? It become positive charge polystyrene ball. Okay, so positive, all the positive will be transferred here. So you already know this plate is positive, right? And this this polystyrene ball also become positive. So positive and positive, what will happen? It will oppose, right? It will repel. So when it repel, it will go back to, okay, it will swing to Q here. Okay. Now when it swing to Q, all the negative charge will go inside the polystyrene ball. So now the polystyrene ball become negative charge. So the negative charge plate and the negative charge of the polystyrene ball, what will happen to them? It will repel again. So it will repel again and it go back to P. Okay. So at P again, what will happen? The positive charge will goes to the polystyrene ball. Now the polystyrene ball become positive. So again, it will repel. So what will happen? It will swing, right? It will keep moving from P to Q, right? So when if this one is when it not touching each other. So what will happen to the EST? The ball does not move. Okay, so mark two forces we attack the on the ping pong ball on diagram. So let's say this one I already explained why. Okay, so a charged ball on the electric field. So this is actually the observation, okay, the one that I told you just now. So when it has T power supply switch on plate P positive charge, so this one will become positive. You have to see, right? You have to see the positive here. So positive means this one is positive. Negative means this one is a negative. So plate P is a positive charge. Okay, so plate P positive charge. Okay, and the plate Q, okay, and plate Q is a negative charge. So since the ping pong ball is neutral, so it's neutral, it remain at the center. Okay, as the electric force acting on it are equal but in opposite direction. So since it's neutral, so it will not move at all. Okay, so now this one I explained also already. So when the metal coated polystyrene ball is pulled, okay, now I pull it, okay, and touch the positive plate. Okay, so the ball will receive a positive charge. Okay, it will receive a positive charge here. Okay, and this one, of course, you already know positive. So positive, positive, it will repel. So it will push the polystyrene ball goes to the metal plate Q. So here the metal plate Q is a negative. So the negative charge will go inside the polystyrene ball here. Okay. Then now it become negative charge. So negative, negative, it will repel. So again, it will swing back to P. Okay. So of course it has to be neutral first, but the negative charge now is sit more than the positive charge when it touch the negative plate, right? So this process is repeated and cause the ball to oscillate between two plates. So it means it has to be the oscillation of the polystyrene ball, right? I think this is a video. See, we see the ball here is swinging. Okay, but they need to use the high voltage. Okay, not the one that we use in the lab. Okay, this one need about like kilovolt. The one that we use is only volt. Okay, but this one, if you want to make it happen, it has to be like almost kilovolt, not volt. Okay, and need to have a high voltage. Okay. All right, so now how to increase the speed of ball. So the speed of ball is increased when the distance between the two plates is increased. So mean we already know V is equals to S over T. So when you increase the distance here, the velocity also increase. Means the velocity, the speed is actually the velocity same. I mean the magnitude, right? So if the mass is smaller, of course, when the mass of ball is smaller, right, the object will move faster. Okay, and the voltage of power supply is increased. So when the voltage increase means the electric field becomes stronger, right, and it has more charge. Okay, so that's why the voltage of power supply is increased. It can cause the speed of ball also increase. All right, the second one, okay, is actually if we use what happen if you put the candle, okay, between two charge, right? Two charge, right? So let's see this video. So you can see there is a part, right? It moves stronger. Later I will see. I will let you see if you got time. Okay. It's the clearer one, right? Okay. So for this part, okay, what will happen to the electric field on the candle flame? Okay, so example, right? Example, if I connected, right? If I connected the two plate here, okay, with the positive terminal and this one is say the negative terminal. Okay. Sorry. If it happen like that, this one is negative, that one is a positive. Okay. So let's say this one is a negative and this one is a positive. So when it goes here, this one should be negative charge, right? And this one should be positive charge. Okay, so actually inside the candle, inside the flame of the candle also they got a charge, right? So what happened here, right? So you already know the negative will attract the positive, correct? So the positive charge will be here, okay? And the positive will attract the negative. So the negative charge will be here. Actually, when you draw, okay, let's say the exam they ask you to draw, okay, to draw the light flame, okay, when you put between two plate, okay, of charge, so it should be like this. Okay, so the one that have the positive charge, okay, it should be at this part. Teacher, why this one is much bigger than this one? Okay, I'll tell you later that one. Okay, so means this one, this negative charge plate will attract the positive and this positive will attract the negative. Okay, now to answer why this one has much bigger, right, than compared to this one. Okay, the flame is much bigger at the left side at the negative plate. Because the positive charge, okay, the size of the positive charge is bigger than the negative charge. So that's why this region the size of flame at this part is much bigger than this side because of the size of the charge, okay, of the positive charge there. Okay, so the flame spreads out into two portions. So the spread of the flame towards the negative plate is bigger, right? So this is actually what is the charge of the plate? So this is positive, right? They give you already, and this one is a negative. Okay, you need to see the label here, positive, and this one negative. Okay, and you have to draw the shape of the candle, okay, when it's placed in the electric field. So you can see here the one that attract the positive charge at this side, you can see the size of the flame is bigger and then this part. Okay, so you need to draw it like this. The positive part is bigger than the negative one. Why? Because the size of the charge is bigger. Then the positive charge is bigger than the negative. Okay, what is the effect of the candle flame on the air around the candle? So around the candle, there will be ionized, no ionized. Okay, ionize the air molecule. Okay, and by referring to the movement of the charge between the two metal plates, explain the shape of the candle flame observed. Okay, so we explain that the heat. Okay, the heat of the flame produce positive and negative ion. So the positive ion are attracted to the negative plate, okay, this one, and while the negative ions are attracted to positive ion. So explain why the candle flame is not symmetrical. So why it's not same? Why this one have the bigger part than the other one? Okay, of course this one is actually the positive ion are heavier because the size of it is bigger than the negative charge, right? So you can see the size of the positive ion is much bigger than negative. All right, so electric current. So an electrical equipment can only function if a current flows in the complete electric circle. So current I, okay, current, what does it mean by current? So current is the rate of flow of charge in a conductor. Okay, rate of flow. So when it means rate, means they have to divide with time. So let's say we learn for the impulsive force, remember the rate of the change of impulse, right? So when you say divide by time, okay, means you have to start with the word of the rate of, okay, the rate of flow of charge. So mean you know that it have to be divided by something, okay. So I is equals to Q over T, okay, Q over T. So this is the formula for current. Or we can simplify it if you want to remember it, like Q is equals to IT. Q is the total charge. So it should be in Coulomb. Okay. So it should be in Coulomb. Charge is in Coulomb. So it's C, right? The unit is C. Okay. And current, of course, you already know ampere, right? And unit, the symbol is A. And time is in second. Okay, the symbol is S. Okay, so this is the formula. Q is equals to IT, right? So Q is equals to IT. And the SI unit for current, there are two. Okay, if you already know I is equals to Q over T, right? So Q is in Coulomb, T is in seconds, so Coulomb per second. Okay, or we can simplify it and put it as a ampere. Okay, so remember the time has to be second. So you need to change it to second if you're, like they give you a calculation question. So you need to change your time to second. All right, current flows. Okay, why does current flows? So the current flows because of the charge flows. So basically, it's actually electrons. Okay, it's the electrons that flows. So the direction of current is opposite to the direction of the flow of charge. Okay, so means you already know direction of current should be, if I say you learn, must be from positive to negative, right? positive goes to negative. You learn in form 2, I think. So it should be positive to negative. But the direction of the electron flows, okay, it actually opposite. It's actually from negative to positive because electron flows from the negative part lah, of course, right? So negative to positive. Okay, but direction of the conventional current is a positive to negative, right? So the current flows from positive terminal to negative terminal. Okay. So what does it mean by what caused the charge to flow? Okay, what is actually make the charge flow? So the current can flows, okay, the current can flows from one point to another point due to the potential difference between 2 points in a circuit. Okay, so there must be a potential difference between 2 points. So then the current can flows. So what does it mean by the potential difference? So it's actually the work done. Okay, the work done in moving 1 coulomb of charge Q from one point to another. So let's say if I want to move, okay, I want to move this point. Let's say the point is the charge, okay, 1 coulomb charge is at A. So I want to move it to B, right? So if I want to move it to B, so means the work done. Okay, how much work that I need to do to move the charge from A to B. Okay, so that is called as the potential difference. Okay, what is the energy? What is the energy I need? Okay, to move the charge from A to B. So this is actually the work done. Okay, in moving 1 coulomb charge from one point to another. Let's say from this one to this one. So this one also is a potential difference. Okay, what is the energy that you need to move, okay, from this point to this point. So that we call it as the potential difference. Okay, so that's why the current can move. Okay, if there is no potential difference, means there is no energy. So how can the charge okay, move? Okay, if there is no energy, because the work is actually in joule, right? So energy also in joule. Okay, so that's why when there is no work done, there is no potential difference, mean the current cannot flow. The current can flow when there is a work done. Okay, there is a potential difference. So mean that's the meaning of potential difference. The work done, okay, to move 1 coulomb of charge from one point to another point. Okay, so this is the formula, okay, for V. Okay, V is actually equals to W over Q or EQ. So I just told you just now, E is actually energy, W is also energy because both of it have the same unit, right? So you can use both of it. So to simplify it, E is equals to QV. So what is V? V is a potential difference, the work done to move the charge, okay, 1 coulomb charge from A to B, let's say as example. Okay, and the work done is the W, okay, how many joule is need, okay, and energy use, okay, what is the energy use, okay, to transfer from point A to B, and Q is the total charge that flows. So how many charge that we make the current flows here. Okay, and the unit should be V is equals to JC. Okay, and basically W and E is the same thing lah. Work done, energy used. So only the V is different. The V that you need to find. Okay, what is the potential difference? And work done energy. So what is the work done or what is the energy used? Okay, to move from point A to point B. Okay, and Q is the total charge. Okay, what is the charge? What is the charge that they say I said this one 5 coulomb charge. Okay, 5 coulomb charge, so means I have to find what is the energy that used to transfer the 5 coulomb charge from A to B, right? Okay, and the SI unit, this one also I think you're already familiar. Okay, so work and energy. So let's say I've used this example. W over Q is actually W is in joule, Q in coulomb. So JC negative 1. All right, so can you join the class point? Wait, I give you the link. Hmm. Yeah, 3.1. Oh, wait. I didn't. Okay. Yeah, I know like some of the class still not finished chapter 2, right? Okay, but some of it we are not same. I think 5M is the, they already until Bernoulli. Okay, I think we already like finished the Archimedes. We are going for Bernoulli 5M. 5K, 5S is not have a different topic, so that's why I put 3.1. Okay, so that one all of you not still not learn, right? So later, don't worry, in the class, we will follow back. Where is your, the last time we learned? Okay, this one is only for the extra class, okay, because we are mixed. The class is mixed, so we need to find one topic that both all class still didn't learn. Okay, we can 2, 4, 3, 7, 8. Okay, so state the meaning of 15 ampere. Okay, so 50 ampere, later I will give you one essay. So 50 ampere is actually the 50 coulomb of charge flows in 1 second. Okay, so let's say if I have 10 ampere, so means 10 coulomb of charge flows in 1 second. Okay, so that's the meaning of 15 ampere. So current flows in a bulb is 0.5 ampere. So I is 0.5 ampere. Okay, calculate the electric current flows through the light bulb in 2 hours. Okay, so now your T is 2 hours. But remember, it have to be in second. So you need to change it to seconds. So 2 times 60. Okay, change to minutes. Okay, and again change to second. So it become 7,200 seconds. Then they ask you to find the electric current flows. Okay, so means you need to find I. So Q is equals to IT, right? Q is equals to IT. So here is you need to just multiply. Okay. Electric current is, yeah. So 0.5. It's actually not asking you the electric current. They ask you for the electric charge. Okay. It's asking you for the electric charge, not the electric current. Electric current is ampere, right? So this one is in coulomb. Okay, so this one should be 0.5 times 7,200. You will get 3,600 coulomb. So this question you can put electric charge. Current is ampere. Okay, electric charge. Charge is in coulomb. Okay, so the answer is 3,600 coulomb. Okay, if one electrons carried 1.6 times 10 power of negative 9 coulomb. So this is the charge. Okay, the charge for the electron. Calculate the number of electron. So we need to use this formula. Q is equals to Ne. Okay, Q is equals to Ne. N is the number of electron. This one they didn't, I think they don't give in the notes. Okay. Okay, number of electron. E is actually the electric charge. E is actually the electric charge. Okay, so your Q, we already have 3,600 here. Okay, and the N is the number of electron that we need to find, and E is the 1.6 times 10 power of negative 19. So you just need to divide 3600 divide by 1.6 exponent negative 19. So you will get like 2.25 times 10 to times 10 power of 22. Okay. So the formula Q is equals to NE, Q is equals to IT, right? V is equals to E over Q. Okay. So that's quite formula to remember lah for this chapter. But some of it they will give in the questions, but remember not all of it. Okay. You already know the one that they give usually is useless, right? Okay. Now I want you to try to answer this one. Ready, give answer, right? Wait, I try to find another, maybe in the questions here. Ah, oh, we already finished one topic. Okay. All right. Um. Okay. So I want you to answer for number 3 and number 4. Okay, number 3 and number 4, then we will stop. We already finished 3.1. Yeah, give 1 more minute. Okay, 3 minutes I will close. So next week we go back on Saturday, 2:30 as usual. Okay. And for the experiment, for 5M 5M, I think we can do the experiment on Monday, but for 5S, okay, for 5S, for Monday we learn as usual in class, okay, because the solution, right, is not ready yet. So guess what? I promise you we have to do the density also, right? But we are not the lab assistant cannot make it like on Monday. So we do it on the next class, okay, for 5S. And 5M experiment as usual on Monday. Okay, the pressure and the depth, okay, of water. So bring your textbook. Right, so let's see the answer. Where's my pen? Alright, so for this one, it says that so I just translate it lah. Right, so the electrical appliance, okay, is switched on for 2 hours, right? And it asks you to find the charge, right? The quantity of charge, so mean the Q here, okay? If the current is 2 ampere, so your I, right, your I is 2 ampere, okay, and the time have to be in seconds, so we already calculate just now 7,200. So you want to find the quantity of charge, you use Q is equals to IT, so you will get 14,400. Just multiply 2 times 7,200. Okay, so the answer is D. Alright, and for this one, the charge, right, the electric charge is flows in circuit, right, in 1 minute. So 1 minute, you already know your T is 60 seconds, and the Q is 3 coulomb. So what is the current here? So again, we use Q is equals to IT. So Q is 3, your I you need to find, and your T is 60, right? Okay. 3, Q is 3, time is, okay, so means, use 1, sorry, this is I, right, you need to find the I. So 3 divided by 60 is,
Teacher,
yeah. Yes, I'm here.
you are not presenting.
Oh, really? Oh my god.
Yeah, it's okay.
Uh, I forgot. Oh yeah, just now I stopped sharing, right? Sorry. Okay. Alright, so this one it says the electrical appliance switch on 2 hours. You need to find the quantity charge, you need to find the Q. They already give you the I here 2. Okay, so this one the 2 hours you need to change to second, right? So I is 2, T is 7,200. Then if you multiply, you will get 14,400. Okay, so this is the 40,400. This is answer is D. Okay, just use Q is equal to IT. And this one is the charge flows in the circuit in 1 minute 3 coulomb. So 1 minute 60 seconds. So your T is 60. Your Q is 3 coulomb, 3. So Q equals to IT. So your Q is 3 here. And your I, you need to find your T is 60. So 3 divided by 60, I got 0.05. So the answer is A, right? So let's check your answer. How you get C? Alright, all correct. Okay, so I think I will stop here. I see you in school next week. Alright, so take care everyone. Okay, happy weekend. Bye.
Thank you, teacher.
Welcome.
Thank you, Chair.
Bye.